So now we'll talk about event loops. Event loops are when you have threads that are divided into main thread, worker thread, and job queue. So if you consider this here, we have the event loop is a stack of tasks or functions to be done, and you get requests that go into the event loop and sit on this stack. And then as workers are available to do some sort of operation like file read, database read, computation, they pull that function or operation off of the loop and operate it on a thread. And in the case of Node, this is done in a way where you don't see or have access to those things. Then the operation completes and puts a notification in. There's kind of like the job queue and I guess the completion queue I should have put in there as well. And so it puts a notification on the completion queue, and the event loop is constantly, it's a function that's basically like a while loop, and it's just constantly checking in a safe way. It has guards in place so that there's not memory corruption. And it checks to see, is there a thread available to do a task? And if there is, it puts it out there. And then it's also checking, is there a result from a task I previously asked to execute? And if there is, then, and the main thread is ready, then it will give that result back to the main thread. And that's what a callback is. So it's, you've got your main thread, which is your JavaScript that you write. All the JavaScript that you write is in the main thread, unless you're doing something like web workers or child processes or something like that, where you are explicitly telling it to use not the main thread, then you're on the main thread. So all the code you put in your app.js is the main thread. Then there are the worker threads. And these are, like I said, unless it's something you specify explicitly, the worker threads are things that are happening in the browser or in Node behind the scenes without you knowing. And this is where all the dangerous stuff happens. This is where all of the memory, the shared memory manipulation is happening, but it's architected in such a way that those problems are mitigated so that you don't have to manage them yourself. And then, as I said, there's a job queue, but there's also a results queue. So there's, I did not put that on here, but I should have. So when you think about Node specifically, there are C bindings to the event loop. So one example I'll give, and I was going to use the Node HTTP library because it's fairly simple, but I just wanted to condense the number of lines of code. So I used request instead. But if you consider this, if you're using the request library, and by default, it actually doesn't return promises, but ignore that. We'll pretend that it returns promises. Promises and callbacks function the same in this way. It goes down to the HTTP library in Node, and then the HTTP library in Node goes to a C binding, actually a C++ binding. And when it hits that boundary, it passes off the task to the event loop. The event loop doesn't live in the JavaScript layer. It lives down in the C++ layer. So it gives a memory reference to a JavaScript object that's translated to a C++ object, which is basically, it's just typed and stuff. It's like, it's more like TypeScript. Actually, yeah, it's kind of more like TypeScript. But so it just passes a memory reference down into that C++ layer below, and that's where the threads are. That's where something gets put on the job stack and where something gets put onto the result stack. So you make the request up in JavaScript, it goes down and down and down and down until it hits the core C++ binding. It gets passed on to the event loop, and your JavaScript continues to execute, and a thread if a thread is free, if it's not already doing work, then the event loop scheduler will take your task off of the queue and put it into a thread that's sitting there waiting, just doing nothing. And then that thread becomes active. And one of the things about this is that in the old model, you'd be creating and destroying threads all the time. So like for every request, you spawn a new thread. After that request is finished, it dies. In the event loop model, you keep a fairly static number of threads. You're not creating and destroying them all the time. You still are, but not as much. You have a much more constant number, and when they're not being used, they're just sleeping. So anyway, the request goes into the event loop. It gets processed in a thread in the C++ world, and the JavaScript continues to execute in the main thread. And the callback happens when the main thread is not busy. So the main thread, in effect, is treated much like a worker thread. When the main thread is not busy, then the event loop looks to see, do I have any references to a callback and a result in my result queue? And if it does, then it hands it to the main thread. Otherwise, the main thread just does nothing. It sleeps while something else finishes. And that's the essence of a callback, is that it goes from C++ land back up to JavaScript land to be executed. So JavaScript, the way that you use JavaScript, functions kind of similarly to a green thread. Well, no, that's not a right description. It functions similarly. Well, anyway, it does one thing. It always guarantees to get a function complete. It will never stop in the middle of a function, except with async await, but that's just syntax sugar around promises, which is just syntax sugar around callbacks. So when you have a function, the function will always complete all the way until its return before the event loop is pinged. And in addition to the C bindings that we find in Node, the other common thing, or in the browser, like fetch is the same way. Fetch goes all the way down to the C++ code. But other common things we have are in Node, we have NextTick. NextTick is interesting because it schedules a function. Node actually has multiple queues in its event loop. And the NextTick queue is prioritized so that literally in the next tick of the event loop, that function will get executed. And that function can put more things on the event loop, but it shouldn't put more things on the next tick section of the event loop, because that's a special section. And if you have a next tick that calls next tick, I could be mistaken, but I believe the actual implementation of NextTick is optimized in a way that it's not guaranteed to happen in the next tick of the event loop. It might actually happen in the same tick of the event loop. So you can get into this problem where the rest of the event loop never actually gets fired because, like I said, there's multiple queues in the event loop depending on their priority. And so NextTick is the highest priority. There might be another method now that's that happens, because there's a way to schedule something at the end of the event loop and there's a way to schedule something at the beginning of the event loop. And I think that there are functions in Node for both now, but I don't quite recall. In any case, this is a special case just for Node.
Are you talking about SetImmediate? No, you haven't got there just yet.
No, SetImmediate.
Hey, AJ, can I jump in real quick about process NextTick?
Yeah, what?
Process NextTick. So it, like in a tick through the event loop, there's like 5 or 7 things that Node does. And in between each of those things, it'll process anything that's accumulated and process NextTick. It's a really unfortunately named function that doesn't actually refer to the next cycle through the event loop, but there are several places within one pass through the event loop that after each of those steps, it'll check the process next tick queue. So it's really unfortunate naming on process next tick because it leads you to think it's the next cycle through the event loop, but it's interwoven throughout all the main work that the event loop does.
Yes. So that's maybe thinking, maybe our conception of what tick is what needs to change for it to make sense.
That could very well be. It clearly doesn't mean pass through the event loop. So tick means something more granular.
Yeah. So anyway, you do want to be careful about NextTick because if you schedule something for NextTick within something that was scheduled NextTick, then you basically do one of the very few conditions in JavaScript that can bring the event loop to a halt. Now, SetImmediate is not that way. If you use SetImmediate will not fire until the next full pass of the event loop. So you can set immediate with inside of SetImmediate without causing the event loop to crash and burn. And in fact, SetImmediate is specified to take at least 4 milliseconds. So SetImmediate is essentially the same thing. No, I'm mistaken about that. SetImmediate is not. Is it that way? I think in the browser it's that way, but I don't think it's that way. I'm getting confused. I should have looked this up more particularly before I got to this point. I forgot some of the nuanced details of SetImmediate, so I might be wrong about the 4 milliseconds. SetTimeout.
Yeah, SetTimeout has a minimum like that, but SetImmediate I don't think it does because I believe the polyfill for SetImmediate uses the promise. The promises have their promise fulfillment has its own queue that that happens like before immediates and other things like that, and so it can happen really fast.
Okay, so I lied about the 4 millisecond requirement, but I'm not lying about the event loop will not be halted if you set immediate inside of SetImmediate because it does actually guarantee the loop, right?
Yeah, Node has some optimizations for what process next tick does if you call it from within a process next tick as well.
Oh, okay.
Before SetImmediate existed, it was the way that you would say, actually, no, really schedule this for the next tick. But it still can cause you to starve. Next ticks always run before IO, and so you can have a really hard time getting IO back if you're constantly processing next ticks. So the event loop is still running, but not in a useful way.
Okay. So, yeah. Anyway, NextTick and SetImmediate are different. There's nuanced differences, and they are at different versions of Node. They behaved in slightly nuanced different ways that could screw up the event loop. Maybe that's been fixed. It sounds like. Moving on to SetTimeout and SetInterval. These are our old friends. Oh, and another thing that I could have mentioned earlier, as long as there's something in the event loop, the process doesn't exit. So if your Node program just prints out console.log hello world, then it prints out console.log hello world, or it prints out hello world, and then it exits, and you're back at your terminal. But if you do a SetTimeout or a SetInterval, if you do a SetTimeout for 1,000 milliseconds, even though your program has nothing else to do because something's on the event loop, the program stays alive for 1,000 milliseconds, does whatever it's supposed to do, and then if nothing else goes on to the event loop, then the process will exit. So SetTimeout and SetInterval do not guarantee an exact number of milliseconds, but they're pretty close. depending on how busy the event loop is, it could end up that it happens a few milliseconds later. And I can't remember if it's ever possible for it to happen a millisecond earlier, but I think it may be possible to happen as much as 1 millisecond earlier. So I think it is possible that if you set a timeout for 1000 milliseconds, it may actually execute in 999 milliseconds, but it's definitely possible to execute in 1005 milliseconds. So that is important to note for applications where timing is particularly important. I have run into situations where milliseconds matter, one of which was creating an audio crossfade that would work when the current tab was not the tab with the audio element. And basically, because when the current tab is not, when the current tab is in the back, or when the tab that your application is in a browser is in the background, instead of having a clamping of 4 milliseconds, which is what SetTimeout would normally have. So if you set timeout 0 milliseconds, it will take at least 4 milliseconds. But that's if you're in the foreground. If you're in the background, it will vary depending on the version of the browser. But I believe that the de facto standard is that the minimum will be 1 second, so 1000 milliseconds. So if you are doing some sort of process like what I was talking about, where you might be playing music or a video or something, and it's not in the foreground, and there's probably better APIs for this now. I'm not 100% up to date with all of the latest audio and video APIs, and like the keyframe APIs, and there's so many new APIs in the browser for this sort of thing. But what I had to do was schedule everything so many seconds in advance, and then cancel the timeouts, like save all the timeouts in an array, and then cancel them if the user made an interaction like hitting pause in the middle of the process happening. But in any case, just important to know that if you run into a scenario where you're say setting 200 timeouts ahead of time and you expect them to be within a certain millisecond, it is possible that they will lag, and I don't think it's possible for them to happen out of order, but it wouldn't blow my mind if you set, one for 50 milliseconds and another one for 51 milliseconds, that it could potentially somehow be possible. I don't think so because of the way the queue gets evaluated, but I'm skeptical. And the last thing that I want to talk about with Node is weak references in the event loop. So by default, everything you do with the event loop is a strong reference in the event loop, which means that your process will continue to wait until all items in the event loop are cleared. In Node, not in the browser, but in Node, almost every API that puts something on the event loop has a method called unref. This is true of child process. It's true of net, which means that it's true of HTTP and HTTPS. It's true of all timeouts. I am not specifically sure that it's true of NextTick, but I'm pretty sure that it's true of NextTick. All of those things that create references on the event loop in Node have an unref. And if you call unref, it'll put it into a different queue, or it'll annotate it. I don't think it actually puts it in a different queue. I think it just annotates it as a weak reference, which means if I call say I call set interval for 50 milliseconds and I print out I'm alive, I'm alive, I'm alive. So every 50 milliseconds is going to print out I'm alive, and I do a set timeout and I do unref on that set interval. So I do set interval, function, console.log, I'm alive, 50.unref, and then I do a set timeout for, say, 200 milliseconds. Then that interval will fire, as long as there's something else on the event loop. So when the timeout reaches its 200 milliseconds and it fires, then that set interval will now be done and it will not fire its next event. Instead, the process will die. So this is really useful if you're designing a database library or certain types of server. If you're using AWS Lambda or Azure Functions or anything like that, it's very likely that you'll have some sort of process at some point that needs to do something on interval or a database connection or an HTTP connection or whatever. And you'll want to unref those. And if it doesn't have unref, there may be something specific. You can just Google. There may be something specific to the library that will cause it to call unref. Like, I don't remember exactly what it is, but I think it was the Mongo library, the Mongo database library. You can give it a special option that's like, don't keep alive, because they didn't call the option unref, they called it something else. But you basically pass in don't keep alive true, and then it will call unref on its, when it calls net to create the database connection, it'll call unref. And that way, it'll only stay connected to the database as long as you've got something else going on. So that is kind of how an event loop works. And it's got some great benefits over just having threads, and huge, like infinite benefits over just having a single process or even multiple processes. It allows you to have priority queues that execute on thread workers. You can, you have more predictable memory consumption. You have more predictable numbers of threads. It basically just, gives you more control and more optimization. Before I go further, are there any questions on event loops or the node event loop? And I'm going to wait a good 15 seconds to hear somebody speak up, because I know I didn't explain that best as I could have.
I have a question.
Yes.
So first of all, thanks for explaining that. It was really clear. Makes a lot of sense.
Oh, good.
So if you could explain in one sentence what the event loop is, how would you do it?
It is a while loop that goes over an array of job queues. And for each, no, let me back up. It's a while loop that goes over an array of worker threads. For each worker thread that is sleeping, it goes over an array of job queues, and until it finds a job to put in that worker thread. Then it goes over, then if the main event loop is sleeping, or the main thread is sleeping, it goes over an array of results and pulls a result from, until it finds a result. It goes over the array of results until it finds a result that's finished and makes a callback on the main thread. Kind of a run-on sentence, but that's what it's doing.
Okay, that makes sense. Thank you so much.
Hey, AJ.
Yes.
So at the beginning, you said that a node program runs until there are no more events to process, something along those lines?
Yes.
How come then if I start a server and it has no request that it's currently processing, why doesn't my program terminate?
Because I should have done an example with not a request, or not only a request, but a server. Because listening is an open queue, so to speak. So if you are listening on a socket, even if there's nothing to well, it's implement, that's libuv. Libuv is what makes it not die, because libuv is the communication between Node and the operating system that handles the specifics of how an operating system determines whether or not a network port is open or closed.
Okay, right on. Thanks.
Yeah, because I could give you Linux specifics or Windows specifics or Mac specifics, but libuv is what makes it not close when there is a network or socket listening. Okay, so are event loops the final frontier? Is Node.js the end all be all? Will we ever need another programming language ever again? Main threads are a bottleneck. And if you listen to JavaScript Jabber, which I'll just put a link to, that is HTTPS devchat.tv, and I'll let you find the JavaScript Jabber link from there. I don't know if the episode got published yet, but if you listen to JavaScript Jabber or if you follow other things going on in the community, excuse me, there's a lot of stuff going on that's been going on for the past several years with the goal of figuring out how to make the main thread not a bottleneck. Because you can bring the main thread to its knees very, 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 very easily. So the main example, oh, whoops, I put a capital P here, my mistake. Too much Golang recently, and I could have blamed it on autocorrect in Google Slides, but it is in fact my usage of Golang that accidentally put that capital P there. JSON.parse will bring the main thread to its knees. Parsing is a very slow operation, and also console.log, because console.log will call JSON.stringify, essentially. So JSON.parse, JSON.stringify, console.log will kill your Node application and your browser application. And if something as simple as taking a string that you just got from a server or just got from a request and parsing it into JavaScript can halt every request across the board, meaning that you can't get events into the event loop and you can't get events out of the event loop because your main thread isn't sleeping. That's a problem. Also, if you were to do something like while true, another common one would be do something like a SHA-SUM or an encryption or decryption operation. Now, Node has since implemented callbacks for hash operations and encrypt-decrypt operations, which you should use, but you will find tons of code that does not use those optional callbacks because the original API was not built that way. But these things bring the main event loop to its knees and mean that ultimately the way that JavaScript works is not a good model for high performance applications with the advances that we have in CPU technology. Having so many cores available and such, we cannot use the cores that we have with the way that JavaScript works today. So the